Things that's neat about the whole sensing business is that it's not one thing, it's lots of things that have to happen to make this work.
Typically, the purpose of a wireless sensor network is to measure some physical phenomena.
For example, there's a mountain fire, and then they quickly dispatch aircraft and then spray the sensor nodes. And based on that, they can draw the boundary of where the fire is going on.
Emerging Science is a Vermont Public Television production in partnership with and funded by Vermont NSF EPSCoR. EPSCoR, supporting science and engineering in Vermont colleges and businesses and encouraging young Vermonters to seek careers in science.
Remote wireless sensors, as the term suggests, measure physical properties and then transmit their information wirelessly. Hi, I'm Amy Seidel. Thanks for joining me on this episode of Emerging Science as we investigate how scientists are monitoring the world around us, both our natural environments and the physical structures we depend on. Today we're focusing on in situ environmental monitoring, where scientists place sensors in specific settings and remotely relay this information. First, let's meet a Vermont scientist who has built a career out of stress, monitoring stress, that is.
My name's Steve Arms. I'm president of Microstrain, Inc. When I was young, an undergraduate at the University of Vermont, I became interested in a field called orthopedic biomechanics, which is basically the study of the joints of the human body. I started working on ways of figuring out how to measure strain in ligaments of the human knee. We were trying to understand what caused knee injuries to try to get a better handle on how they could be prevented, possibly with sort of, for one thing, better ski binding equipment, for example. We didn't really know what the strains were, how the ligaments of the knee strained in different kinds of conditions. And the big reason why that information wasn't known is the sensing technology to make those measurements was not very good. So I started making sensors as a grad student and shipping them to different parts of the world for other researchers to use to study other parts of the other orthopedic biomechanic problems, spine and shoulder and ankle and all kind of things. This is the tibial component, and this is the femoral component. When the femur presses down onto the tibial component, there's sensors in here that actually can pick up those loads. And I'll show you what they look like on here. This is a structure that's been machined to be sensitive to the pressure exerted by the femur against the tibia. And there's little tiny strain sensors they look like little black grains of pepper. They are called piezoresistive strain gauges, and they're extremely sensitive, and they provide an output that is basically the loads in 4 locations right here, 1, 2, 3, 4. Now inside the stem, this stem goes down into the tibia. That's where the electronics lives, and it basically takes the analog signals from the sensors and converts it into a digital data stream and wirelessly transmits it out of the implant. And then the patient could do things, and we could find out what types of activities put strain on the anterior cruciate ligament and what types of activities did not. We've received, I can't remember the exact number, it's probably 6 or 7 phase zeros, totaling $60,000 approximately. And we've leveraged that into somewhere in the vicinity of $5 million in federal funding. This is another application that's pretty interesting that has strain gauges on it. This is a part from a helicopter. This is called a pitch link or a control rod. And the purpose of this component is as the helicopter is flying, it's spinning round and round and round, and its job is to change the angle of attack of the rotor up here. The Navy asked us if we could monitor the loads on the pitch link wirelessly because they're spinning round and round. You can't attach wires to the darn thing. The other problem that the Navy asked us to overcome was to make it so that we don't have to power the device with batteries. How do we do this? The science of it, how does it work? Well, there's a board, we call it the pitch link board. It lives underneath all this protective covering. And attached to the pitch link down here are strain gauges, and those strain gauges are set up to measure the tension and compressive loads that this thing sees. This piece here is a piezoelectric material, and piezo means stress in Greek. When the link sees cyclic strains, that generates power. In here are lots of little fibers running along the length of this, and those, when we apply tension to this, those fibers have a polarization, and that polarization creates voltage when it's stressed. But as long as you keep this stuff moving, it's going to keep generating electricity. That allows the pitch link board to acquire the loads data, record it, and transmit it perpetually without any need for battery maintenance. What's important about the pitch link and why the Navy wants us to measure its loads is when helicopters are undergoing aggressive maneuvers, turns and pulling up very rapidly, these loads, the loads on this link go up 8 times that of straight and level flight. So if you're measuring the loads on this component, you're not only learning about it, but you're learning about the loads on all the rotating parts of the helicopter. Currently, most of those components are replaced solely on the basis of flight hours. With a tracking system, you would be able to replace those components based on the fact that they've actually accumulated damage and need to be replaced. Well, there's lots of systems that need to be monitored. Many of our bridges could use monitoring systems, for example. Here's a webcam, and you can see what's going on with the structure. So what the webcam allows you to do is to get strain information and correlate it to what's happening to the bridge at the time that strains are being monitored. I think the way to approach it is to put sensors on critical structures and in key areas. We think by the time the structure's cracked, it's probably too late. So as accumulated damage occurs, we know how rapidly that damage is accumulating. And that allows us to anticipate well in advance that a crack might start to form. So the philosophy here is stay ahead of it, stay on top of the problem, and keep track of that damage. And we have developed very good electronics and sensors that, combined with the appropriate mathematical model, can make the world a safer place. It's a great way to contribute.
Monitoring bridge strength took on a heightened priority after the disastrous collapse of the highway bridge in Minnesota in 2007. Monitoring bridge strength introduces us to the concept of in situ wireless sensing. This is the placement and remote tracking of sensors in any environment.
The term remote sensing is used actually, you kind of from afar, you sense what is there. That's mostly from a satellite perspective. And what we call the in situ sensing is that to put a device in the environment and directly actually sense the data, sense the environment around it, and send the data back.
The heart of our computational architecture for collecting and reporting the data are these motes. You can think of this as a tiny little computer, really. It has a processor, it has memory on which you can store data, but it also has an antenna from which it can send or receive data.
What we're interested in, project that we're working on, is looking at how much water there is in snow. And as we know out here in Vermont, the snow falls and it's great, the things ice over, right? And so you can't just look at how tall, how high the snow is. You really have to understand more about what the water content is. The importance of knowing water content in snow is to understand spring runoff, for example, impact on agriculture, erosion, things like that.
We could also have networks, say, of these snow water equivalent sensing devices, and they could all be communicating their information back to a single sink where all of the data will be stored, either if I bring the sink up with me or if it exists on site. The advantage of using wireless sensor networks is lower cost, much lighter weight, and ease of deployment. The state-of-the-art is a SNOTEL site, and this is a really large 10 by 10 foot rubber bag filled with a couple hundred gallons of antifreeze that measures the load that's on top of it. That information is then stored on electronic data loggers. The 200 gallons of antifreeze is very heavy. The snow pillow is very heavy. You have to dig to install the snow pillow, etc., etc. So it's quite an undertaking to install one of those sites. We're developing a new sort of sensor technology based on attenuation of electromagnetic radiation. As a remnant of the Big Bang, the universe is still flooding the Earth with gamma rays. Although these gamma rays will pass through just about anything, they are stopped to a certain degree by water. We can measure gamma ray spectra in a particular area. As snow builds up over the gamma ray detector, I can measure the change in the gamma ray spectra, and from that I can extrapolate how much snow is on top of it. As the sensing device is reporting its data, it's transmitted electronically to one of these devices, and then this device can either store that data on board for later collection, or it can transmit data over a radio. So having an understanding of what a snowpack is essential to natural resource planning.
Researchers at UVM are developing this remote sensing strategy to understand the quantity of water in our snowpack, a critical issue here in Vermont, considering spring runoff and the agricultural needs of the state. This technology will prove even more important in other parts of the world.
It turns out that the snowpack, especially along the Sierra crest, is absolutely essential to life there. It's where California gets a large amount of their water from. So one of the real goals of our project in making these lighter, cheaper, easier to deploy, more accessible, is to improve the granularity of measurement. That is, if they're cheaper and easier to deploy, we can have a lot more of them out in the field. And this gives us a much better view of the physical phenomena that's actually out there.